Good morning. This is Kavipriya, Assistant Professor, EC Department, SNS College of Technology. I am going to discuss about the topic divergence, divergence of a vector and divergence theorem. Before starting with the discussion, let's recall about the gradient. So we all know electromagnetic field consists of both electric and magnetic components. So these components vary with position and time. So we require a tool for analyzing these components. So one such tool is a gradient. And I'm going to discuss about what is the concept of divergence, what is a mathematical expression, physical significance, divergence in EMF, divergence theorem, and finally about the applications of the divergence. First, what is a divergence? So divergence is one which measures the spreading or a convergence of a vector field. So it indicates whether the particular vector field is a source or sink based on the spreading and the convergence. So when we apply this divergence to a vector field, we'll be getting the output as a scalar. So it is represented as del dot. Here the vector is taken as A. So it is represented as del dot A. And next is the physical significance of a divergence. If the result of the divergence is positive, then the particular vector field is a source. If it is a negative, then it is a sink. If the result is a zero, then the particular vector field is a solenoidal vector field. And next is a mathematical definition of this divergence. So for any vector, here we are taken as a Cartesian coordinate system is taken as an example. For any vector A, in Cartesian coordinate system, the components of a vector is represented as x, y and z. Here it is ax, ay, az. So when we apply divergence to this vector field del dot A, the equation for this is dou ax by dou x plus dou ay by dou y plus dou az by dou z. We'll be performing a partial derivative on the particular vector field. And the result of this divergence is a scalar. So unit of this divergence is purely depends on the vector. And next is a divergence in an electromagnetic field. First, let's discuss about divergence in the electric field and then about the magnetic field. So when we apply divergence to the electric field, we'll be getting a result as rho by epsilon. Rho is a charge density, epsilon is a permittivity. And when we apply the divergence to the magnetic field, we'll be getting the result as zero. So it indicates the absence of magnetic monopoles. And next is a curiosity challenge. First one is an odd man out. The equations given as del dot del cross A. So divergence of curl of a vector is equal to 0. Second one is a curl of gradient of a scalar is 0. Third one, divergence of gradient of a scalar is 0. And final one, divergence measures a net outward flux. Among the four, the odd man out is third one. So del dot del phi is equal to 0, where this del dot del is nothing but it is an del square operator. So it becomes del square. Del square phi is equal to, del square phi will not be equal to 0. It is a Laplacian operator, will always not equal to 0. Second riddle is, I measure how much leaves a tiny cube, and if I am 0, nothing is lost or gained. I connect volume and flux in a powerful theorem. Who am I? Which is nothing but divergence. Divergence is one which connects the volume and the surface, and it also connects the flux. So net flow of flux will be equal to the divergence of a volume integral of divergence of a vector. This is a divergence theorem. And next is about the divergence theorem. As I told you previously, divergence theorem is one which relates the volume integral and the surface integral. So it is one which converts a volume to surface, surface to volume. So it is very useful in electromagnetic field analysis. So the explanation is nothing but the net flow of flux over any closed surface is equal to volume integral of divergence of a vector field. So here the V indicates a volume and S indicates a closed surface. It is one which relates a surface integral and the volume integral. And next one is the applications of a divergence theorem. It is used in the derivation of Gauss law and it is used in the calculation of electric flux. So net flow of flux over any closed surface is being get calculated in this divergence and used in a field analysis of the capacitance, and it simplifies the electromagnetic field equations. And this is a summary. I have discussed about what is divergence, physical significance, mathematical definition, finally the applications, and before that I have discussed about the divergence theorem. These are my references. And finally, assessment. Divergence of a vector field at any point represents the net flow of flux per unit volume. A vector field is said to be solenoidal when when a divergence of a vector field is equal to 0, then the particular vector is a solenoidal. That's all about the divergence and divergence theorem. Thank you.